Hi, everyone. Welcome to the 7th lecture of CS 188 for this semester. Let's start with a couple of logistics. Homework 3, Games, has been released. It'll be due on Monday, this coming Monday. And just also a reminder that every homework has 3 parts that are due. There is the electronic homework, there is the written part, and then there is the self-assessment of the previous homework. For the written and for the self-assessment, make sure to use the templates that we provide. Any questions about that? Yes? Yeah, for the self-assessment, you can go into Gradescope, download a PDF that you submitted, and annotate onto that. If you happen to not submit anything, you can grab the empty template and annotate that with the differences between what you had, which it would be empty if you had empty, and annotate it with everything we have to show the differences. You can annotate it electronically, or you can annotate it on a printout and then re-scan or take pictures, but we want you to use the templated format. Whether you do it by writing or by directly electronically. Project 2, Games, is out. In Project 2, you get to program minimax, alpha, beta, evaluation functions, Expectimax, which we'll see today, for Pac-Man to play against ghosts. This will be due next week, Friday at 4 p.m. Also, there's an update to the homework policy. We already posted this on Piazza, but I don't think we've said it in lecture yet. There's 11 homeworks total, which is more than usual. You also have 3 parts to each homework, which is more than we've done in the past. So we've concluded it makes sense to let you drop the 2 lowest scoring homeworks. So at the end of the semester, we'll automatically look at every subset of 9 homeworks and see which one gives you the highest score and use that one to compute your homework grade. You can independently drop written versus electronic versus self-assessment, up to 2 of each. You don't have to drop them. You can just also do them all. But our calculation will then still just try to grab the 9 highest scoring ones and give you a grade based on the 9 highest scoring ones for each separately. Any questions about that? Yes? Say it again? The written homework is graded based on whether you completed it. Our mindset here is that with the written, we want you to work on it as if it were an exam, let's say. Give yourself a feeling of where you would be at if it were an exam. Then after that, maybe talk with some other students and write up after that your full understanding of everything. If it looks like you completed everything as you would do in an exam, then you will get a complete grade on the written, whether it's accurately solved or not accurately solved. The self-assessment, similarly, you will assess what the difference is between your answer and our answer, but our assessment of your self-assessment is based on whether your self-assessment is accurate, not based on whether your self-assessment gives you a 0 or a 5 or a 10. Sorry, I couldn't hear that very well. What do you mean with the lowest scores? So what will happen is at the end of the semester, there will have been 11 homeworks. And for each one of you, we will look at your 11 electronic homeworks, see which 9 out of 11 have the highest score among your 11. And those 9 will constitute your electronic homework score. Then we'll look at your 11 written homeworks. We'll look at the 9 out of 11 that have the highest score. Use those as your written homework score, and then we'll look at your 11 self-assessments, and we'll see which 9 out of 11 have the highest score there, and use that as your self-assessment score. Any other questions about that? Mini contest 1 is ongoing. It's optional. It's a lot of fun, though. It ends on Sunday. Let's take a look at the leaderboard at this point. So this is what the contest looks like. You'll have massive mazes compared to the ones you've done in the regular project. You'll have multiple Pac-Man agents that work together to clear the board, and you'll be time constrained, or better phrase, time penalized. The more time you spend thinking about what to do, the lower your score will be. Let's take a look at the current leaderboard. At number 1, we have currently Otto. Is Otto here? Over there? Great. At number 2, we have Jason here. Great. And number 3, we have Yunshen. Yunshen here? Yunshen? I think Yunshen wasn't here last time either. But Yunshen has a good entry in the contest. And at this point, there's, I believe, about 140 teams on the leaderboard. Some teams have 1 student behind it. Some teams have 2 students behind it. Also, some fun names starting to emerge. Too Greedy. Team No Sleep. Don't recommend that. A name for the leaderboard when you're just too tired to come up with something. Joe Mama. KiwiBot. Just got some food delivered. Should have tried harder. And many more. We'll take another look next time. So this will end on Sunday, and then next week we'll report out on the results of the final ranking and also on the strategies used by some of the top teams. Any questions about the mini contest? Okay, let's start with the technical content for today then. Today we're going to look at decision making when there is uncertainty, and we'll also start looking at what these utilities really are that we've been optimizing all along since lecture 1. So, we'll now have uncertain outcomes. Remember this game tree from last time where we had a maximizer player at the top, gets to choose between 2 actions, then the minimizer gets to choose, and we see a 10 and a 10 on the left, a 9 and a 100 on the right. If we run Minimax, what do we end up with? Minimax will say this would be 10, this would be 9, so we should go this way. And that's what you want to use if you play against a true Minimax player that really optimizes, in this case, against you. You want to take no chances because they're going to stick you with a 9 on the other side. But we also alluded to, what if you play against, let's say, an agent like this one? Maybe if the agent looks like that, you say, I'm willing to take my chances. There is a possibility that they don't play the optimal thing for them, and that would give me 100. And a 9 is not that much worse than a 10, so I'm just going to go for it. But that was pretty informal. And the question today becomes, how do we formalize something like this? It could be an agent that looks like that, and you say, I'm willing to take my chances. It could also be that there is inherent stochasticity. Somebody's going to be rolling dice, and based on the outcome of the roll of the dice, go left or right in that bottom branch. If that's the case, and let's say chances is a coin flip, chances are 50-50, then you could say, well, on average here, I'm going to get 109 divided by 2, so 54.5. On average here, I would get 10, and now we have a formal way of justifying going that way, because on average, we'll do better going to the right than going to the left. When we do this kind of calculation, we'll have a different kind of scheme of annotating the nodes. We'll use circles. So we had up triangles for the maximizers, down triangles for minimizers, and we will have circles for chance nodes. Okay, so when we follow this procedure, it's called Expectimax search. You might ask yourself the question, why wouldn't we know what the result of an action would be? how come there could be a chance node in our model of the world? Well, one possibility is that it's designed that way. Maybe we're playing a game, and as part of the game, there is some dice being rolled, and then it's by design stochastic. Another possibility is that the opponents we're playing with are unpredictable. So we don't know how they're going to act, and maybe we can model them with a probability distribution over possible things they might do. And we think that maybe modeling them with a probability distribution is a better way to model them than to model them as masterminds that work against us. Another reason it could be that what this is modeling here is that first you get to choose between two actions. After you choose those actions don't get executed perfectly. Maybe you're a robot, you want to spin your wheels a bit, and you expect you're going to move forward or backward, depending on which action you take. But then the wheels might slip, and you might actually not move forward or might actually not move backward, but instead stay in place. And then the chance node here would model the fact that after you chose your action, the outcome of that action is actually not deterministic. Now, when we're in this stochastic world, our value should reflect the average case, which is the Expectimax value, rather than the worst case or minimax outcomes. When we run Expectimax search, we will compute the average score under optimal play. So optimal play here means that you maximize what you get on average. What does that mean? In a game like this one here, you would still, if you choose the right branch, always either get 9 or 100. You would never get the 54.5. That's never an outcome of the game. But what we're saying is if you were to play this game many, many, many times, and you take the right action and it's really 50-50 there, then on average you'll get 54.5. Hence we call the value of the top node the Expectimax value 54.5. Even if never we actually experience that specific value in any single outcome of the game. How does the algorithm work? Well, the max nodes are just like in minimax search. Nothing different has to happen. Chance nodes are like the min nodes. They're our opponents in some sense, but they're not working against us. It's just stochastic. And so rather than saying in a chance node we take the min, like we did for minimizers, in a chance node we say let's take some weighted average based on how likely each outcome is. Those are called expectations, the weighted average of the outcomes. Later, we'll actually see another formalism that's very related to this that's going to start next week called Markov decision processes, which is another way to think about Expectimax problems. Okay, actually, let's run some demos illustrating what we're doing here. So, as typically in the lectures, there's kind of two big parts to how we think about problems. We have the world, we want to turn it into some model that we use of the world, and then we have an algorithm that works on the model and finds a solution based on that model. And so you can ask the question, okay, what does it mean to model the world in a very specific way? For example, let's model the world. Let's go back to a situation we had last time. Over here, very grim world again for Pac-Man, flanked by two ghosts. We now have a choice on how to model the situation. We could say we're going to model it as ghosts that work directly against us. That would be minimax. If we model things that way, then we have a minimax tree where there is Pac-Man, then each of the ghosts, then Pac-Man, each of the ghosts, this repeats, and we have a tree that goes maybe till the end of the game. If we do a minimax search in that tree, what will happen? Well, we saw last time, because we lose a point for every time step that passes, and we again tend for food pals, but we're flanked here and we're going to be eaten by the ghosts. We might as well be eaten as quickly as possible. So we're going to go right on to the red ghost and get eaten as quickly as possible. And that's indeed what minimax in this case will give us. So minimax in action, go straight to the nearest by ghost, minimize the damage. What, on the other hand, if we set it up as an Expectimax tree? In Expectimax, when the ghosts choose, it's a coin flip. In particular, for the blue ghost, it's a coin flip whether they'll go up or down. And then they keep going the direction they chose. So if we run Expectimax, what do we expect to happen? We say, well, just two possible outcomes. well, there's many possible outcomes. If we go to the right, only one thing happens, we die instantly. If we go to the left, there is two possible outcomes. Either the ghost is running away or coming to me. If it's coming to me, then I'm in trouble, and I really should have dive-bombed the red ghost. I would have finished things off earlier and lost less points. That's a bad outcome. But if the blue ghost is running away from me, then I can run behind the blue ghost, eat all the dots, and get high reward. So, Expectimax will then say, okay, if that's a 50-50 thing, we now need to average the score you get in one case versus the other case of running to the left. And if the average of that is higher than what you get from running to the right, then you should run to the left. That doesn't mean after you decide to run to the left that you're guaranteed to do better than you would have done if you had run to the right. It's a 50-50 chance. And so sometimes you'll do really well, sometimes you'll actually not do well. Depends on the random seed. Let's see what happens here. Expectimax was run. Pac-Man has decided, needs to go left to maximize expected value, but will it be lucky in this run or not? We'll see. It is lucky in this run, and so it gets a very high score. If we run this again with Expectimax, it might be lucky again, or it might be unlucky this time. It's unlucky, and it has a score that's as negative as it's going to get in this particular game scenario. But on average, it's doing better than if it had gone off to the right and ran into the ghost instantly. One thing that's important to keep in mind here is that we're making assumptions about how these ghosts function, right? And these assumptions can be mismatched with the world, and we need to be careful about that. If you run Expectimax, but the ghost is actually playing against you, then you're very naive and you're going to be taken advantage of. On the other hand, if you play Minimax, but the ghost is kind of random, then you're very pessimistic about everything, too cautious, and you don't take advantage of opportunities. And so it's important to understand how the world functions to then decide which model you're going to use. Here's a pseudocode for this. Looks a lot like the Minimax pseudocode we had last time. There's a dispatch node. The dispatch node decides, is this a terminal state or not? If it is, return the state's utility. If it's not, check, is it a max? Call max value. Is it an expected node? Call the xValue function. This one is the same as before. Then the one on the right, the expectation calculation, is a weighted average. So it loops over all successors, looks at the probability of that successor, and then looks at the value of that successor, multiplies it with the probability of having that successor, and computes the weighted sum of all of them. So let's take a look at this in action. Here is a exp node. We have probabilities that are not equal in this case, 1/2, 1/3, 1/6. So that means we end up with 1/2, 8, plus 1/3, 24, plus 1/6, -12, which is, 4 plus 8 minus 2 is 10. So we have 10 over here. And again, very different from Minimax is that in Minimax, whatever ended up over here corresponded to something we had at the bottom. Here, there is no 10 at the bottom. You're never going to have 10, but on average, you expect to score 10 if you land in this node. Let's do another example. Maybe let's have you work through this one. Give you 30 seconds, talk to your neighbors, and figure out what is the Expectimax value, that is the value of this node over here in this game tree. All right. Any thoughts on the value of the game here? Anyone? Suggestion is 8. Anybody have another suggestion? Everybody thinks 8 seems right. How will we get 8? Well, it wasn't explicit here. When it's not explicit, we tend to assume that all probabilities are equal. We could sometimes have them not be equal, but we're assuming they're all equal. It's nothing else is said. We have to then equally average these. 3 plus 12 plus 9 is 24. Divided by 3 is 8. 2, 4, 6. That's 12. Divided by 3 is 4. 21 divided by 3 is 7. Then we have a max node on top of that. Max node will choose the maximum expected value, which is 8. So we had it right. Now, last time when we looked at minimax, after we saw minimax, we saw some modifications of minimax that could make it more practical. For example, we saw alpha-beta pruning, which was a meta-reasoning approach that allowed us to think about, is this subtree important to look at, or does it maybe not even matter what's in this subtree? It's not going to affect the outcome of what the value is of this game. Can we do the same thing here? We have an Expectimax tree. We've seen the left branch to be 8, so we know that we have an option of 8 going this way. We now see a 2 over here. Can we now skip the rest or not? See some no's. Why not? Well, you can't know. Right now it doesn't look pretty good with a 2, but what if one of these is 1 million over here? All of a sudden it looks really good, and you want to go there. Of course, you still need to check none of the other ones are negative 1 billion. But it really matters to look until the last one, because when you average things out, one really extreme number can always dominate the average, and so you can't skip anything in this scenario unless you know there are maybe some bounds on what values can be achieved at the different nodes. So can't do the same kind of pruning. The other thing we looked at was to do a depth-limited search. The reason there was that if we have to traverse the tree, even with alpha-beta pruning, where we only need to look at, in best-case scenario, square root of the size of the tree, square root of the size of the tree is still often way too big to visit everything. So can we maybe look at less by making approximations? And in depth-limited search, we made the approximation that we said, we're not going to search all the way to the bottom, because we can't get there in the time we have. We're going to stop earlier. So maybe we stop somewhere here. We say after 3 moves, we use an estimate of the true value using a evaluation function. So we'd look at the current situation. We had an evaluation function that says this situation we think is worth this much. Compute that number and use that instead of looking underneath. That evaluation function is only going to be an approximation. It might be better if you design a really good evaluation function, worse if you don't design a good one. A lot of art goes into that. Often also machine learning goes into that. If you have seen many situations before, you've seen how much they were worth, you can in principle machine learn to predict how much a new situation is worth. What it results in is that you don't need to go as deep in the tree, and you can, in a reasonable amount of time, find an approximate answer to the value at the top. Okay. How about these probabilities that we're using now? Let's do a little bit of a refresher of what they are, and then build up from there. A random variable represents an event whose outcome is unknown. And a probability distribution is an assignment of weights to those outcomes. For example, we might decide that we don't know what the traffic is on the freeway or Bay Bridge right now. We don't know what it is, but we still want to somehow reason about it. And so we're going to assign probabilities to different possible situations. We might say 25% chance it's empty. It's probably not the Bay Bridge, then it's something else. 50% chance the highway has mild traffic, and 25% chance it has heavy traffic. A lot of modeling assumptions being made here. For one, we just assumed that traffic can take on only 3 values. That's a very specific assumption of how we're modeling the world here. You might say, I'm going to measure density with real numbers. or you might say, I'm going to model it in 5 categories. Those are choices you have to make as the engineer, the designer of your AI system. How do you want to capture what is in the world? And then the second thing we had to do is choose probabilities for each one of them. And the choice of those probabilities will affect what we do when we run an Expectimax agent. Because if the probabilities are different, then different outcomes are more or less likely, making certain branches better or worse for the agent. But that's what we have to do here for now. There are some laws of probability. They're always non-negative, and they have to sum up to 1. So notice that the sum of all of these is 1. It's also the case that as we get more information, maybe over the lifetime of the agent, the probabilities can change. For example, maybe a priori we think probability of heavy traffic is 25%, but now we know that it is 8 a.m. Well, if we know it's 8 a.m., probability of heavy traffic is higher because a lot of people are driving around 8 a.m., and now the probability has changed to be 0.6. We'll talk more about that later. The middle 1/3 of the class is very much focused on dealing with probabilities, updating them based on new evidence that comes in, and so we'll defer that to them. But for now, just keep in mind that these probabilities are things we need to work with and that they can change as you get more information. What does it mean to compute an expectation? The expected value of a function of a random variable is the average weighted by the probability distribution over outcomes. So how long does it get to the airport? How long to get to the airport? If this is our distribution over traffic, and maybe depending on the traffic situation, it could be 20 minutes, 30 minutes, or 60 minutes, then the expected value of travel time to the airport would be the weighted sum, which gives us 35 minutes. Any questions about this? This is kind of the basic review we're doing. Yes? Okay, so the question is, what if the expected value is the same in both branches? But maybe in one branch, it'll be either 500 or 550, whereas the other one would have something closer to 0 and 1,000, and that's much higher variance. Might you have a preference for one or the other? We'll touch upon some of that at the end of this lecture. So let's defer that for now, but it's a good consideration. So in Expectimax search, we have a probabilistic model of how the opponent or the environment will behave in any state. This model could be as simple as a uniform distribution, roll of dice. Model could be sophisticated and require a lot of computation. You might say, it might be something along the lines of, you have to decide whether to organize a barbecue or a indoor event on maybe October 10th. And then maybe you run a complicated simulation of air pressure, airflows, and from that you have a distribution over what the weather will be like on that day, and then you use that distribution to decide whether one or the other is the better decision. And so that can often happen in practice, that the way you get those probabilities is after very complicated calculation, and then finally you know what the probabilities are. In the game tree, there's a chance node for any such stochastic event where we don't have control. It could be opponent or it could be environment. And it might even be that our probabilistic model says that it's likely the ghosts are adversarial to us, but they're not necessarily always adversarial to us. That's one type of probabilistic model, where you say maybe they're mastermind ghosts working directly against us, maybe not, maybe some probability for one, some probability for the other. For now, we assume each chance node magically comes along with probabilities. So probability fairy visits us for this lecture, sprinkles the probabilities, and we're good to go. One thing to keep in mind, though, is that even though this is how we model things, it doesn't need to mean that we are right. For example, you might model a opponent as some probability of being minimax and some probability of being random. But that doesn't mean the opponent is actually doing any such things. It's just your model that you put in this Expectimax tree, and hopefully your model is related to what is happening in the real world. For example, maybe you're playing against someone and you don't have enough information to know how they play. You don't know their strategy. And then you might have a distribution over strategies. In practice, they have one strategy and they're using it, but you don't know what the strategy is, and so you have a distribution over strategies and optimize against a distribution over strategies rather than a single strategy. Let's do another little exercise. Let's say you know that your opponent is actually running a depth 2 minimax and uses the result 80% of the time, and the other 20% of the time doing a random move to mix things up. How would you put this into a game tree? I'll give you about maybe a minute to think about this, talk with your neighbors, and let's see what you come up with. Okay, any thoughts about how we can model this? Over there, yes.
I'm not too sure, but since our opponent makes random moves 20% of the time, like to leverage that, I feel like we should also have like some percentage of the time when we take risks to assume the opponent's random move is like a terrible move for them, but really good for us. So like a little bit of random, and then try to do the max for the rest of it.
So the suggestion here is, because we know the opponent periodically makes a random move, we don't want to play too conservatively, and so we want to somehow build into what we do that we don't end up playing too conservatively. Now, of course, the question is, how do we build that into it? So we know that's what we want based on analyzing what the description is here. But what we want to avoid, of course, is that we have to hard code all kinds of things into it, and we'd like to see if we can reduce it to a game tree. And if we run search, the right kind of search in this game tree, then that strategy that you want, that periodically taking your chances, just automatically emerges from solving the game tree. And so the question becomes, if we want to achieve this, and you're right, we do want to achieve this, how do we set up the game tree such that a search in that tree gives us what we want? Suggestion that in the back there? Okay, so the suggestion there is, if we reach an opponent node, we're going to model it as 80% chance one type of behavior, 20% chance another type of behavior. The 20% chance other type of behavior, in fact, we reach a chance node again because it's random. And the 80% side, we reach the minimax strategy of depth 2 that the opponent is using. And then once we do that, and that's the answer we're going to follow here, is we achieve a game tree that if we run Expectimax in that game tree, we find a strategy that takes advantage of the randomness in the opponent while also being aware that it's only random 20% of the time. So the answer remains then Expectimax. But to run this Expectimax, when we look at these chance nodes, for each chance node, a bunch of calculation has to happen inside that chance node before we can proceed. So when we look at one of these chance nodes, what's the probability of the opponent, let's say a ghost, moving left or right? Well, we need to then look at this description here, and we actually need to go run depth 2 minimax to understand what happens 80% of the time. So you need to think about that. That tells us for 80% of the time what's happening. One specific action, depth to minimax solution. And then the other 20% of the time, we have maybe equal probability over all other actions, or maybe even including the one that's chosen from the depth to minimax. So what we have here then is that whenever we encounter a chance node, we have to do a whole minimax calculation to just find the probabilities that live in that chance node. Imagine the ghost did a depth 10 minimax, then every chance node you encounter, you'd have to run a depth 10 minimax search, which could be pretty expensive quickly, to find the distribution over actions they would take. So it's kind of interesting. Imagine it's indeed depth 10 minimax 80% of the time, and 20% of the time just random action. To solve that kind of problem, in every opponent node, you have to run another depth 10 minimax. Whereas regular minimax, you just have to do depth 10 once in the original tree and you're done. What's happening here? Why is it so much more expensive to deal with an opponent that does this other thing where sometimes they do something random? It's because now we don't have a perfect match between the assumptions of one player A about player B, and player B about player A. Once these assumptions are mismatched, all of a sudden the tree doesn't nicely align in the entire search, and you need to do all these side calculations. And that's what's happening here. Whereas in minimax, if one is always minimizer, other one is always maximizer, and they know that about each other and do that consistently, then their tree is the same tree. But here it's not anymore because there's a mismatch, and we need to do a big calculation in each of the opponent nodes to figure out what they would do in that situation, or distribution over what they would do. Any questions about this? Yes? So the way we set it up here, the assumption is that this is how we model the opponent. So we model the opponent as doing this. What they actually do, it might be that. If it is that, then we're doing great by solving it this way. If they're actually doing something else, then doing this is not going to be the best fit to play against that opponent. But all we can be sure of in this setting here is that we have a model for how we think they behave, and if we assume that's a good model, this is how we could solve the problem. Question? Yes? In this case, it will take a constant amount of time longer. So it'll be the constant amount of time that it takes to expand depth to minimax search. And so maybe that is a certain amount of time that is a factor, 20 or 100 larger than just already having a chance node that tells you distribution over actions. And then that would be happening throughout the tree, that you have to pay that factor 10 or 100 whenever you consider the opponent. It also shows that in practice, you might have to approximate your opponent, because if your opponent is somehow capable of looking 100 deep, you might not have the resources to also look 100 deep, and you'll have to approximate it with something else that hopefully is good enough. Let's take a look at the assumptions we're making throughout here. And what are the dangers of optimism and the dangers of pessimism? What are the dangers of optimism? It's assuming chance when the world is adversarial. What does that mean? It means you go around the world, you see everything very rosy, everything's good. And in practice, that might mean you get pickpocketed everywhere, you get mugged, a lot of things go wrong because you're just assuming the world is so good where it really is not as good as you're assuming it is. And so that's the danger of optimism. You get taken advantage of by adversaries. What's the danger of pessimism? Well, what does it mean to be too pessimistic? It means that you assume the worst case when it's actually not that likely. Like, you see a bunny and you think it's a vampire bunny. every single bunny you see. Now, that gives you a very, very scary life. You're constantly jumping away from things, not living very optimally if they're just kind little bunnies. More generally, what it means, let's look at some examples for Pac-Man. What we'll do here is we'll look at a grid of possible scenarios. So what do we have here? We have Pac-Man could play Minimax or play Expectimax, and the ghost could be adversarial or could be random. If the ghost is random and Pac-Man plays Expectimax, that's a good way to play. You're kind of matched up with how the world works. So let's take a look at that first. Random ghost, Pac-Man plays Expectimax, and here we go. The ghost randomly stepped out of the way. Pac-Man didn't. Let's watch that again. Pac-Man assumed the ghost would do something random, so wasn't afraid to get too close, and then just ate the one pallet left and won the game. What do you think is going to happen in the next one where we have Pac-Man play Minimax and the ghost is adversarial? Well, adversarial ghost is going to try to chase Pac-Man, and Pac-Man is going to anticipate that and keep a safe distance and hopefully still somehow get to the food pallet. You might wonder, how come this adversarial ghost doesn't just protect the food pallet? Wouldn't that be a smarter thing to do? Well, that's what an adversarial ghost would do if they could look really, really far ahead in the game tree. But in practice, we can only look so far ahead. The typical evaluation function for a ghost is based on distance to Pac-Man. And so if you only look, let's say, 4 steps ahead, and after 4 steps you're hoping to be as close as possible to Pac-Man, then you get this kind of behavior where you are constantly trying to move closer, and you might open up the pallet for Pac-Man to eat and finish the game. Now let's think about what happens if we assume, well, we play Expectimax, but the ghost is a Minimax ghost. So the ghost is playing directly against Pac-Man. Pac-Man is playing Expectimax. So Pac-Man is too optimistic for their own good. So very optimistic, hangs out, and just made it on this one. Sometimes optimism is good and it works out. Sometimes it's less good. And so this will play out stochastically because just the way the game is set up with a little bit of randomness in it. And sometimes Pac-Man will succeed, sometimes be eaten. It's not playing very safe against an adversarial ghost. How about the other scenario? The scenario in the bottom right here. Not bottom right. The random ghost, but then a Minimax Pac-Man. Minimax means Pac-Man assumes the ghost is playing against it, so it's going to play very safe. Assume that ghost has a plan to come and chase it and eat it, and going to keep a very safe distance. But in reality, the ghost is actually random. So the ghost is just randomly bopping around. Pac-Man waits off on the left, and then when finally there is room, is daring to go. Let's look at another one of these. Ghost is just bopping around. Pac-Man is worried. He's very worried. Keeps being worried, but then finally says, now there is no mastermind plan that exists anymore that can get me on the way to the dot, and now I'm willing to go. We ran this quite a few times. Here are the scores we ended up with. So if you want to get statistically significant scores, you need to run more than 5 times, but I think this gets the picture across. If it's a random ghost and Expectimax, we get the highest, on average 503, because we're in an easy environment, because the ghost is not playing against us, and we're aware we're in an easier environment and taking advantage of it. Here, we're in a difficult environment, and we're aware of it. Our score is lower, but not that bad, because we realize it's a difficult environment, and we play accordingly. On the other hand, if it's a difficult environment and we're not aware of it, then we often get eaten, and our score is not that great on average. And then over here, we have a random go, so easy environment, but we're not really taking advantage of it, so we have a lower score than if we take advantage of it, but not that much worse in this case because we only waste so much time being scared before we dare to go for the food pallet. Any questions about this? Okay, so far we have seen two types of games. We have seen Minimax games and Expectimax games. There are some other types, still turn-based. For example, backgammon. In backgammon, there is a maximizer, a minimizer, and chance. And so, effectively, this is the same thing. We just now need a dispatch node that can dispatch between terminal, max, min, exp, and we can solve these kinds of problems too. For example, what happens here? It's maximizer's turn, chooses a move. After that move, there is a roll of dice, which determines the situation minimizer gets to see, in which they get to make a move, and this process repeats. Very simple in terms of algorithmic change, just four-way dispatch instead of three-way dispatch. Backgammon is actually a pretty big game in terms of state space. There's about 20 legal moves each time. There's a depth. If you do a depth 2 search, then you have 20 moves, but there is also this stochasticity to account for how many possible outcomes of rolling the dice. And we get actually a very large tree, even if we only look at very small depth. As the depth increases, probability of reaching a given search node shrinks. So what we have happen here is that because of the stochasticity, each particular branch is in some sense less significant than it would be in a minimax scenario. Because in minimax, maybe the opponent could force us down a path. In backgammon, the opponent can't really force us down anything. They need to have the right roll of the dice before they can force us anywhere. And so no single branch can dominate as much as it can in minimax. Historically, what that resulted into is that for backgammon, it was actually the first AI world champion for any game. This was built with just a depth 2 search, a very good evaluation function, trained with reinforcement learning, and this achieved world champion level play. And so the intuition here, why you can get away with a depth 2 search, is that if you miss this one scenario that could happen somewhere down the tree, actually it's not that likely to happen anyway because of the averaging that's happening. And so just depth 2 happens to be enough to build a world champion. There are other types of games. So this is one variation where you have min-max exp. Here we have a multi-agent game. So we have a red player, a blue player, and a green player. What does this mean? It means if we're at a terminal node here, let's pick one where they're all different numbers. If we end up over here, the utility for red is 7, for blue is 2, for green is 1. So what we have here is that each player has their own value of a terminal node and will optimize for their own outcome. Minimax, we kind of had that too. The maximizer had the number that we were showing, and the minimizer had the negative of that number. So there were actually two numbers sitting there, but it was the negative of each other, so we only showed one. But minimax is a special case of this, where we just collapse those two opposite numbers into one number that we display. Different things can emerge here, though, when these numbers are not just complementary to each other. For example, what if we're over here? What would blue want to happen? Well, blue would love this 6 over here. Can they make that happen? Well, what if they play this way? What will green do? Green will look at, well, I could have 6 or 2. Green will choose the 6, which will happen that blue also gets 6 and gets what they want. So what we have here is actually a collaboration between blue and green. Happens to emerge because the utilities they have over outcomes happens to be aligned in a nice way that they end up working together. That doesn't mean they are told to work together. It's just emerging from these utilities. If the game ended up over here, what would blue want? Blue would say, well, I'd love to get a 7. That's the nicest thing underneath here. Let's say blue goes here. What will green say? Well, there's a 1 here for me and a 5 here for me. I like the 5, I'm going here. And blue ends up with 2. Blue really should have gone this way, where green would have chosen, let's see, actually, not sure if it fully works out here. Blue would have preferred, let me retake that one. What happened here on the right is that even though blue would have preferred 7, green doesn't pay attention to that and just picks this one independently. What happens on the left is something very similar. If blue goes here, green will still not pay attention to what blue cares about. Here's a 7, here's a 2, and green will pick this side and blue will end up with 1. And so in both branches here we see that green picks the opposite of what blue would have wanted, even though on this side they're perfectly aligned. And that's just a consequence of whatever their utilities are for the leaf nodes. How do we solve a problem like this? In each node, we now look at the values underneath and pass them all up based on the decision the current node would make. For example, we're here. Green checks 2 or 6. 6 is better, so it's being passed up. 1, 6, 6 is being passed up. Here, green says 2 is better than 1, so 6, 1, 2 is being passed up. Then blue takes a look, which is the middle number. 6 is better, so 1, 6, 6 is the value over here. Similarly, on the other side, green decides at the bottom, we'll go for the 7. This is a 5, 1, 7. The other one will pick the 5. This is a 5, 2, 5. Then blue will pick based on the middle number, so it'll be a 5, 2, 5. And red will pick on the first number, and so it'll be 5, 2, 5. And this is how the game will play out. So similar machinery as we've used for min-max and expected nodes, but now keep in mind you need to propagate values for all players, not just a single value. Any questions about this? Okay, let's take a couple minutes break here, and after the break we'll look at utilities. Sure.
So you don't have predefined office hours, right? We should email you?
They Okay, let's restart. In the second half of the lecture, we're going to look at utilities. If you think back to lecture 1, the kind of mantra for the AI class is maximize your expected utility. We've been maximizing expected utilities. We've not actually looked at those utilities and where they might come from and why it's even meaningful to have them, should they even exist, and that's what we're going to do now. So, one question you could have, why should we average utilities? Why not minimax? Okay, let's think about this. Let's say you're going to make a decision, and maybe you're deciding between, deciding between pizza and Thai food or something. You might say, okay, what are my utilities for each one of them? The Thai food is exciting, but it's sometimes too spicy for me, and then you might assign some utility to it. The pizza has some utility, but the Thai food one has like different outcomes, so you could say, well, I should maybe use the worst case, where it's too spicy for me, and it's going to be bad, so then Thai food is a worse choice than pizza, and I'm going to take pizza. That would be the minimax approach to choosing what you're going to do. But maybe that's not the right way to do it. If you're constantly afraid of the worst-case scenario, that's the scenario we talked about. Everything is a vampire bunny. In fact, what you're then going to do is you're never going to go out on the street. You're going to say, there's always some chance that one of the drivers makes a mistake, drives onto the sidewalk, hits me. And your minimax tells you to stay inside at all times. Then it'll maybe say, well, if you're inside, maybe an earthquake can happen and things can collapse. And you'll just have no reasonable choices if you run minimax for all your decisions. The only time minimax can actually be useful for you is if you already ahead of time exclude all those really special things that rarely happen. But if you want to incorporate that these things can happen, these extreme events, then minimax will never work. So if you want to do fairly comprehensive reasoning about the world, minimax will just not work for you because you're always afraid about what's going to happen. Okay, so then effectively we're down to something like Expectimax. What's the principle of maximum expected utility is that the rational agent should choose the action that maximizes its expected utility given its knowledge about how the world works. Okay. So, then the questions are, where do these utilities come from? Let's think about that. Let's say you have an agent that's supposed to clean your house. Where should the utilities for the agent come from? Well, we should specify them for that agent. We should tell the agent, your utility is based on how clean the house is. We can't just let the agent choose their own utility. If they choose their own utility, they might just say, oh, well, high utility no matter what. I'm just going to sit here. It's easy. I'm optimizing my utility. Have to do nothing. So to ensure that the agent does something we care about, we got to be able to give it the utilities that we want it to optimize for. So that's where they come from. We have to give them to the agents. But that means that somehow we have to have utilities that quantify what we like or don't like about outcomes in the world. So how do we know that we even have those? And that's even rational to have utilities. Does it even make sense to think of the world in terms of every outcome has a utility associated with it? And let's say we do have a number for every outcome in the world. Why is averaging them the right thing to do? And what if you believe that your behavior just doesn't match up with utilities? Is that possible? Is it possible that you just live your life in a way that utilities are not meaningful, and then maybe you can't use utilities for your agents to help you out because it's mismatched with how you live your life? Well, let's first take a look at some of the new challenges in Expectimax in terms of utilities compared to Minimax. Let's look at these two game trees here. What's different between them is that we squared the terminal values going to the right. So 0 squared is 0, 40 squared is 1600, 20 squared is 400, 30 squared is 900. Now let's see what happens if we run minimax in both of these trees. Well, let's run in the first one. What do we end up with? Well, we end up with a 0 here, a 20 here. So we're going to play this way. What's going to happen in the second tree? Outcome's going to be the same, because by squaring, the leaf nodes have the same ordering, so we have the same preference over leaf nodes. And in Minimax, that means we end up with the same outcome. Min will still prefer going left there and still prefer going left here, which will make max prefer going right here. The value is now 400 because we squared everything, but the game gets played the exact same way. What if we have expected nodes there? Well, this average is 20. This average here is 25. 25 is better. We have 25. How about on the other side? The average here is 800. The average on the other one is 650. So we prefer the 800, and it has changed. So by squaring the utilities, we've changed how we play the game. So it means that all of a sudden when we work with things like Expectimax, where we average utilities, it's not just about ordering outcomes, it's also about the numbers we associate with these outcomes, because the specifics of those numbers do matter and affect what we're going to decide. Okay, so let's look at some examples. Our utilities are functions from outcomes, that is states of the world, to real numbers that describe an agent's preferences. For example, maybe there's 3 possible outcomes. You have an ice cream cone. You have an ice cream cone with 1 scoop. That's probably better. Or you have an ice cream cone with 2 scoops, which you might think is even better. And so you might say it's this kind of preference relationship. That's great, but if we want to do Expectimax, it's not enough to know which outcome is preferred over which outcome. We actually need to associate numbers with each one of those to reason appropriately. Okay. In a simple game, the numbers are easy. They're just the rules of the game will tell you maybe +1 for a win, -1 for a loss, 0 for a draw. It turns out there's a theorem that even beyond games, for any rational preferences, we can summarize them with a utility function. And we'll see the theorem in a moment. Okay. So, we prefer 2 scoops over 1 scoop over just a cone. But when we make decisions, we might not get to decide just between those 3. There might be probabilistic outcomes. For example, we might get a single or a double. Single makes us pretty happy. Double is more complex. When we get a double, we might drop it, much harder to balance, and now we only have the cone. Or we might really be happy and have the 2 scoops to enjoy. Now if we need to decide whether to go for single or double, it matters what the probabilities are of us dropping it, and it matters what the actual utility numbers are here. It's not enough to know that 2 is better than 1 is better than 0. We need to know the numbers and the probabilities, and that will determine which choice we make over here. Okay, so we need to deal with utilities of distributions over outcomes. Outcomes here, the terminology that people use is prizes. Don't think about it as some kind of prize you win for something amazing you've done. It's just terminology. You can just call it outcomes or leaf nodes in one of those trees, and there could be a prize that's called A, one that's called B, and so forth. A lottery is a situation with uncertain prizes, so it's a expected node over outcome could be A or B. And then our notation is that if we prefer A over B, we write this. If they're equally good to us, we write this thing. Okay. Now, when we talk about lottery, again, this is a terminology in this context that means something specific. This is what it means to be a lottery. It doesn't mean there's some kind of game involved where you're scratching things and seeing what's underneath. It just means that a probabilistic event is going to happen. We end up with either A or B with some probability distribution. Okay, now let's see what it means to be rational. Okay, one thing we want from a rational agent is that it has transitivity of its preferences. What does that mean? If the agent prefers A over B and prefers B over C, the agent should also prefer A over C. That seems pretty logical. can we make this even more explicit, that this is really the only right way to go in some sense? Well, we can. Imagine we have an agent who does not satisfy this property. Then we can essentially acquire all their money. The way this would happen is that if they don't satisfy the property, let's say they prefer B over C, then if they had C when they start out, they would happily pay a little bit of money to give us C, and in exchange get B. And we get 1 cent along the way by giving them B and getting C. If they then prefer A over B, then they just got B from us. They can give us B now and pay a little extra to get A instead from us. And we again made some money. They now have A. Now remember, we got C from them initially. If they're non-transitive, they decide C is better than A. And we have C ready to go, and they'll give us A again with a bit of money, because C is worth more to them. Now they have C, and we got some money, and we're back to where we started. So we went around in a circle where, at the end of it, all that happened is we made 3 cents, and everybody's holding the same prizes as they were holding in the beginning. So being transitive seems pretty important. Otherwise, this cycle is going to be kind of put into play against you, and you're going to lose everything over time. What are some other axioms that people have posited rational agents should satisfy? You are required to either prefer A over B, B over A, or be indifferent to them. Those are the only 3 options for 2 prizes. Transitivity, we just discussed. Continuity, if you prefer A over B and B over C, then there must be a lottery between A and C that is equivalent to B. Because B lies between A and C, so some distribution over A and C should match up with B. Substitutability. If A and B are equally good to you, then a lottery that involves A with some probability is equivalent to you to the same lottery that involves B rather than A. Monotonicity says that if you prefer A over B, then if P is a probability that's higher than Q, then a lottery that has higher probability on A compared to this one here should be preferable. Okay? Because you prefer A over B, you increase the probability of A, then you should prefer that lottery that has increased probability of A and decreased probability of B. These all seem pretty logical that you would want from your agents. There is some theory that shows that if your agent's preferences satisfy, or your preferences satisfy these actions with rationality, then your optimal behavior can be described as maximization of expected utility. Okay? So rationality confirmed if you satisfy these axioms, and a more formal theorem says this, that this is the von Neumann-Morgenstern theorem, and also from Ramsey in 1931. Given any preferences satisfying these constraints, there exists a real valued function u, the utility function, such that if your preference is A over B, then that function u will satisfy u of A bigger than or equal to u of B, and the utility of a lottery will be the weighted sum of the utility of each of the entries, each of the prizes in the lottery. This is what we're doing in Expectimax, right? The averaging step is exactly this. We're averaging utilities based on their probabilities. So this is saying that that is a right thing to do if you have rational preference. So if you're happy with these axioms, then the consequence is that there exists a utility function where averaging is the right thing to do. The maximum expected utility principle is then to maximize that expected value. Let's now think about human utilities, because if we're going to have agents make decisions for us, we need to think about our utilities and give them to the agent so they can maximize our expected utility. How do you assess utility values for outcomes? One way to do is to normalize them. You could say the best possible thing in the world is a 1, and the worst possible thing in the world is a 0. For example, maybe worst thing is being dead, and then you could start quantifying this as things like micromorts. If you have a 1 in a million chance of death, what is that worth to you to avoid that? Okay? You start quantifying things that are extreme, because we want to look at the extremes. Quality adjusted life years is another metric often used. It's also important to keep in mind that when we say there is a utility function consistent with your preferences, you can actually add a constant to it and rescale it with a positive scalar, and nothing will change in your behavior, because that is compatible with how averaging operations also work out. Okay. Now, if we don't consider lotteries, all we can do when asking people questions is understand what they prefer over what and have a ranking. But once we start giving them lotteries, we can start understanding the actual utility values. And that's what we need to do to infer their actual utility values. So here's how we do this. Standard way of getting somebody's utilities, you say, okay, you can spin the wheel or pay to pass. When you spin the wheel, there's some small chance it lands on death, instant death. That's it. Okay? So nobody would like to play this game probably. But the question is, how much are you willing to pay to not have to play this game? And that tells us something about what, let's say, this is worth to you. So, best possible prize is, in this case, could be life stays as is or something. Worst case is you're dead. And so the game would be, you could say, okay, how much would I be willing to pay to avoid death? Well, maybe I'm willing to pay $30 to avoid death. If it's some kind of micromort thing where there is, let's say, a 1 in a million chance of dying. If that is your decision here, what that means is that on the scale from 0 to 1, on this standardized utility scale, $30 to you is worth 0.000001 micromorts. Okay? 0.001 morts, which is 1 micromort. So we now have a scale. That's how much you value $30. We can do this for everything. For everything, we can say, okay, maybe you ask, how much do you value your laptop? And you might say, well, maybe there's a choice or something else. Maybe how much do you value getting a new bicycle? And then you might say, okay, there's a choice between getting a new bicycle or playing this not having to play this game. And then you say, well, I'd rather play the game and get the bicycle than to not play the game. You look at the equivalence, what probabilities land on here such that you're equally happy with one situation versus the other, and that tells you the utility value of a bicycle, a new bicycle for you. How about money? Isn't money a way people measure utility? It turns out money is not the same as utilities. For example, let's say we have a lottery. Some probability of winning X, 1 minus P probability of winning Y. Then the expected monetary value is this quantity over here. That's averaging the money. But the utility of this lottery is this over here. So the utility of the lottery is the weighted sum of the utilities of each outcomes, which is not the same as the utility of the average money you would get. In fact, often the utility of the lottery will be smaller than the utility of the average money that you would get. That means most people are risk averse, and when deep in debt, people tend to be risk prone. Let's make this a little more explicit. Imagine you want to understand utility of money. This is money. This is utility. How much is money worth in utility values? Well, who wants $1 million? Most people. Some people don't. You missed your chance. Pause. Okay. Now, $1 million means it's worth something positive to you because you like it. Okay. How about $1 billion? A lot of people. Whoever doesn't want, come talk to me. Maybe how much is it worth to get $1 billion? Well, worth more. How much more? Well, maybe some amount more. Now, let's think about it again. Now you have your $1 billion in hand. Do you still want $1 million? Yeah, probably you still want $1 million. More is always better. But the first million is much more special than once you already have the billion. So the additional value here from utility you get from going from 0 to $1 million is much higher than if here you got an extra million, maybe and only end up over here. And so we see that somehow when you look at these utility curves, they end up kind of starting to saturate. Not saturate, but climb more slowly as you have more. And then kind of the other way around here. Once you're in debt a lot, once you have lost $1 billion, you cannot pay it off ever anyway, most likely. So what is it to then lose a little more? It's all the same. And so that's what's happening on this side over here. How can we quantify this? Imagine there's a lottery between $1,000 and $0. What is the expected monetary value? $500. But most people would prefer a guaranteed other amount. Would you prefer $10 guaranteed over the lottery? Probably not. Would you prefer 900 guarantees over the lottery? Yes, definitely 900 guaranteed is better than this. How about 400? Maybe 400, because it's guaranteed, and on average you get 500, and 400 is pretty close, and now you're guaranteed. Turns out that's where most people will land, around $400. So what that means is that the certainty equivalent lies lower than the average. That's where insurance companies come in. If you are holding a lottery ticket of this type, an insurance company will say, this is worth $400 to you. I'll buy it off of you for $400. I'll take the ticket. The insurance company now has a lottery, but it has so many lotteries in its pool of lotteries that central limit theorem kicks in. And for the insurance company, that averages out, and that lottery ticket is actually worth $500. Even for you, it's the equivalent of $400. And so that's how you actually get a win-win situation, where there's a difference between the $400 and the $500. That's where the opportunity lies to have a win-win. In fact, if the insurance company gave you $450, they would still make $50 on it. And so between $400 and $500 is the wiggle room for negotiation, where all the win-wins lie between you and the insurance company. Now let's take a little test. Let's say you can choose between lottery A or B. A is 80% chance, $4,000, 20% chance, nothing. B is guaranteed $3,000. Who prefers A? Who prefers B? Most people prefer B. Here's another lottery. Choice. C, 20% chance, $4,000, 80% nothing, versus D, 25%, $3,000, 75% nothing. Who prefers C? Who prefers D? So most people preferred C. That is actually pretty typical for general population to prefer B over A and C over D. So slides also predicted that. Now, let's do a little bit of math. If a utility of $0 is 0, because we can shift and rescale anyway, then B better than A means utility of 3K is better than 0.8 utility of 4K. If C better than D, then we have this equation over here. That's the exact opposite statement. So people who prefer B over A and C over D have reached a contradiction. What does that mean? It means, as far as this is concerned, you had irrational preferences, because there's no utility function that can satisfy both at the same time. Or maybe there is. Maybe it's not that you're irrational. Maybe there's something else at play. When you look at the utilities, and people study this paradox a lot, they say, well, maybe it's not because people are irrational. Maybe it's because we don't model the situation the right way. Maybe what happens, the reason you prefer B over A is because when A is being chosen, and you end up over here, you don't just get 0, you also get a very, very stupid feeling that you could have had a lot of money and you didn't. And so there's a 0 plus stupidity here. And the utility of 0 plus stupidity is lower than the utility of 0 and makes it all work out again. All right, next time we'll look at MDPs.
I find this stuff really interesting, so I was wondering what